There's a bug report so absurd it became a legend among engineers. A university reported that email would not travel more than 500 miles. Not 500 megabytes. Miles. As in geographic distance. Think about how insane that sounds. Email is data. Data doesn't have a tape measure. There is no line of code anywhere that says, if the recipient is far away, refuse to deliver. And yet, that's exactly what appeared to be happening. The punchline to this story is one of the most beautiful in all of computing. Because the real cause wasn't software superstition. It was physics. The speed of light, multiplied by a timeout, comes out to almost exactly 500 miles. Let me walk you through how that's possible. The story comes from Trey Harris, who was running the email systems for the statistics department at the University of North Carolina in the mid-1990s. One day he gets a call from the chairman of the department. The chairman says, "We're having trouble sending email to anyone more than 500 miles away." Trey, understandably, assumes he misheard. Email doesn't care about distance. He asks the chairman to repeat himself. And the chairman repeats it, deadpan. A geographic statistician in the department had actually been measuring the failures. Emails to nearby cities went through. Emails to faraway cities bounced. He'd plotted it. The cutoff was a radius of about 500 miles. Now, if you've ever debugged anything, you know the feeling in Trey's stomach right now. This violates everything you believe about how computers work. But here's the first lesson: when a user reports something impossible, they're usually describing a real symptom with the wrong theory. The distance wasn't the cause. It was a clue. Something in the system correlated with distance, and Trey's job was to find what. So he starts investigating. He tries sending mail himself. Local addresses, fine. He sends to a spot a few hundred miles away, fine. He sends further out, and it fails. The pattern holds. This is not a hallucination. To understand what happens next, you need to know one thing about how email is delivered. When you send a message, your server opens a connection to the receiving server and has a little conversation using a protocol called SMTP. Your server says hello. It announces who the mail is from. It announces who it's for. The other server replies at each step. It's a back and forth handshake, and it all has to happen fast enough before your server gives up waiting. That last part is the key. Every step has a timeout. If the remote server doesn't respond within a certain window, your server assumes something's broken and abandons the attempt. Trey digs into the mail server software. It was a program called SendMail, notorious for its cryptic configuration. And someone had recently, accidentally, upgraded part of the system. Here's what happened. The operating system had been updated. That update quietly reinstalled SendMail, but with the machine's carefully hand-tuned configuration file replaced by a fresh default one. The old, custom configuration had a generous timeout for the opening handshake. The new default configuration set it to almost nothing. Effectively zero. The server would send its greeting and wait only a heartbeat for the reply. Now connect the dots. When you talk to a nearby server, the reply comes back almost instantly. Well within that tiny window. But when you talk to a distant server, the signal has to physically travel further down the wires. And signals, even through fiber and copper, are bounded by the speed of light. There is a hard physical limit on how fast a reply can come back from far away. Beyond a certain distance, the round trip simply takes longer than the timeout allows. So the near servers replied in time and the mail went through. The far servers couldn't reply fast enough, the timeout fired, and the mail bounced. The failure really was a function of distance. The chairman was right. But does the math actually work? This is the part that gives every engineer chills. Let's do it. Trey figured the misconfigured timeout was roughly a few milliseconds. Call it about 3 milliseconds of budget for the round trip. Light in a vacuum travels about 186,000 miles per second. In fiber and cabling it's slower, but let's use the round numbers. Multiply the speed by that tiny time window, then remember the signal has to go there and come back. Work it through and you land at a maximum reach of roughly a few hundred miles. When Trey ran the real numbers against the actual timeout value, the answer came out to just under 500 miles. The physics matched the bug report almost exactly. Sit with that for a second. A statistician with no access to the server had, by plotting bounce failures on a map, accidentally measured the speed of light through the campus network. He reverse-engineered physics from a broken inbox. This is why the story survives. It's not just funny. It's a perfect lesson in debugging. The most impossible-sounding bug you'll ever face is impossible only because your mental model is incomplete. Every layer beneath your code is still physics. Electrons and wires. Photons and glass. Latency that grows with distance. We build such tall towers of abstraction that we forget there's a real, physical world holding it all up. And notice what the distance really was. It was a proxy for latency. The user saw miles. The truth was milliseconds. Correlation pointed at geography, but causation lived in a timeout setting nobody knew had changed. That gap between symptom and cause is where every hard bug hides. The junior instinct is to dismiss the weird report. The senior instinct is to ask, what invisible variable moves in lockstep with the thing they're describing? There's one more lesson buried here, and it's a quiet one. The bug wasn't introduced by a developer writing bad code. It was introduced by a routine update silently overwriting a config file. The most dangerous changes are the ones nobody chose to make. So next time someone hands you a bug that couldn't possibly be real, don't laugh it off. Believe the symptom. Doubt the explanation. And remember that somewhere under your abstractions, the universe is still keeping time.